Câu hỏi mình khác. Thế bắt đầu bị cảm giác rồi.
Hello. Morning. So it is our last lecture. And yeah, very next week we will learn the thermodynamics. So we finish the course in mechanics today. And so let's start. We're still in chapter 4. Okay? And now we continue with the energy and energy preservation. First, what is energy, right? Energy. So, energy is the what you think every day. You use every day, right? Out energy and more energy, something like that. So what is it? Energy is the capacity to do work, and it is measured in joules. So the units of energy is related to the name of the scientist. His name, I don't know, joules or something like this. And then you have the law is Joule length, and that Joule is related to that thing. Okay? So the unit for the energy is joules. And energy exists in different form. So you have the kinetic energy, what we mentioned from the previous lecture, when I mentioned the kinetic energy conservation during the elastic collision, right? So the first form is the kinetic energy, and you also have potential energy, light energy. Okay? Thermal energy. Thermal energy is thermal you will have for the next course. In the fundamental physics one. Electrical energy, right? Electric. So the energy, so the name of the energy is related to the source of the energy. So electrical energy is the energy from the source, is from electricity, right? And the thermal energy is from the heat and something like that. It's a thermal energy. And nuclear energy. So nuclear energy is very powerful, right? Have you ever heard about this? Nuclear energy is bomb. Nuclear bomb, and they can produce. And nuclear energy also they use to transfer the electricity in some country. For example, France is a famous country to produce the electricity from the nuclear energy. So in this course, we care about two types of energy. That is the kinetic energy. That is called mechanical energy because our course is mechanics. And then we care about the mechanical energy. And the first type of the mechanical energy is the kinetic energy. So what is it? So we pay attention to the kinetic energy, and kinetic energy is the energy that body poses during its motion. So the formula is 1/2 mv squared. So from the formula you see that the kinetic, if you want to have kinetic energy, you need to have the mass, right? Any object having mass, moving with some velocity, you have the kinetic energy. Okay? And if you are at rest, the kinetic energy is 0. Okay? If you are moving, you have kinetic energy. Otherwise, no. Of course, almost of the object having mass, right? The problem is whether it's moved or not. If it's moving, you have the kinetic energy. If it doesn't move, you say it's stationary or it's at rest, and in this case, the kinetic energy is 0. You don't have this energy. The second type of the energy is potential energy. Potential energy is the energy stored in an object due to its position and state of the shape. For example, this guy, when I bring it to this height with respect to the floor, I say that it's propose some energy, okay? And then we call this energy is potential energy. So the energy as object is this position is not the same as this position. They are different. Okay? Because if you are at a very high altitude, when you fall in, you think that you have more energy. And you feel it's not safe when you are very at a high level, right? You feel it's not safe because when you increase the height, you pose more energy. And more energy, and then you tend to transfer to another type of energy, and then you feel not stable. So if I'm standing on the floor, and then I choose the origin to calculate the potential energy is 0 at the floor. So when I'm standing on the floor, I feel safe because it's stable, more stable, right? Then I'm at this level. It's very easy to hold up, right? But I'm not. Okay. That is the potential. So it depends on the position. If it depends on the positions of the objects, so it means that the potential energy depending on the displacement, okay? Position. And the kinetic energy depends on the velocity. So two types of the energy in the mechanics depending two kinematics. That is the position of the objects and velocity of the objects. Okay? For example, potential energy, you have gravitational potential. Last in my previous example, okay? So gravitational potential is the potential energy you have because of the gravity. Because it's turned to move. Because of free fall motion, that is the gravity, that attractive force of the Earth to the object. So you have the gravitational potential. So in case of the spring, you have the elastic potential. Because when you make the spring extend or compress, on the springs you both some energy. Okay? And later you know that the potential energy is related to the force to act on the objects. And the kinetic energy is something related to the velocity, the motion. And you have the energy conservation. Energy conservation means the energy can be converted from one form to another form. So you can convert from kinetic energy to potential and vice versa. For example, you have this object. It's falling, right? Initially it's at rest. It pulls some potential energy. So the kinetic energy is zero. And the potential energy is some value, right? And I release it. So it's moving down. And at this point, it's moving, right? So it has some velocity. So it means that from this point to this point, the kinetic energy is increased, right? And how about the potential? Potential is decreased because the height is lower. So in this case, you can say that the potential energy from the initial place is already converted, some of the potential converted into the kinetic energy. This example telling you that this type of the energy can convert to another type of the energy. So who can tell me another example where you see the energy can change from this type to another type? As you see in the derivative. Example? More example? You see in the derivative? Reference? Reference?
Yeah, it's a transfer from, it's converted from the electric to the cold.
Yeah. That is thermal energy, right?
Yes.
Electricity. Okay. Electrical energy to the thermal energy. Very good. Thank you, Lâm. Any other example? You see? In your life, around your life.
Yes, TH elevator.
Elevator, yes. Electricity. To?
To motion. Kind
Yeah, and sometimes it creates some wind, right? Kinetic energy, okay?
the line.
The light.
Yeah.
The light is from the electrical energy to the light energy. Very good. From the electrical energy to the thermal energy. Very good.
The heating system is really transferring the electricity energy into heating.
Can you speak louder?
The heating system.
The heating system. Changing the electrical energy to the heat, right? Very good. Thermal energy.
Solar panel.
Solar.
Yeah.
Yes, solar energy.
Transfer from solar to the electricity.
Very good. Of course, from the solar to the electricity, it has some exchange between the mechanical energy, right? Mechanical energy inside and then to create the electricity. Very good. Thank you. So you see that the conclusion is the energy exists in many types of the energy. And for the energy is conserved. The energy you cannot create, it's changing from this type to another type. Okay? It always changes. If this guy is increased, so making the other guy decrease, and vice versa. And some of them is constant. If you don't lose the energy. And I introduce the concept is called efficiency. So what is the efficiency? Efficiency is a fraction of useful energy output divided by the total energy input. For example, if you use the electricity to cook, to boil the bottom water, okay? So of course, the total energy is electricity you measure, and this total electrical energy not convert into heat. Not only heat, but also not only heat to boil the water, but also some heat go around. Yeah. So you lose some heat for the outside, from the air to the air, right? So the useful energy is what? That is the heat to use to boil the water. That is the useful. And the loss is the heat go out of the air, and total is electricity. So the fraction of the useful energy divided by the total energy is called efficiency. So what is the useful energy depending on the purpose? Okay? So in some case, you think this guy is useful, and this guy, another guy is not useful. But the same guy in just another situation, maybe is useful energy. So who can give me some example? You understand the question? So the energy is useful or not useful, depending on the purpose, right? The same guy in this situation is not useful, but another situation it is useful. So who can give me an example? No?
Some example about the waste energy the electric line from the electrical factory
Okay.
transfers to our house. Some of the electric is waste during the
Transmission.
Yeah, transmitter in the electric line.
Okay. And some other case it is useful. When you need the light.
Yeah.
When you need the light, so it becomes useful. Okay? Very good. Or you, in my example, when you boil the water, so if you think you need to boil the water, so the energy to use to boil the water is the useful. But there are some purpose. In the winter, you need the heat around to make warming up the room.
Yeah.
So in this case, the energy go out is useful energy, right?
Yes.
Because you care about it. So in this case, it's not the waste energy, but it's useful. Because you need to warm up the room, okay, the house. All right. So be careful, right? The same guy is not always useful, and not always depending on the purpose. So when they ask you to calculate the efficiency, you already think about efficiency for what? For which purpose? Okay? And then so that you can define what is the useful energy. Any question? Otherwise, we move to this part. So now we look at example for the energy conservation during free fall. Okay, during free. So you go back with the problem of the free fall motion, the object. Alright, so look at here. If you consider the free fall motion, so assuming that you have ground level is here, and then you're considering an object with the mass m at the height 8. Okay, so moving is moving here, and then you consider 2 points. You consider this point A to B. So the object's moving from A to B. At the position A, the velocity of the object is v1, the velocity vb is v2. Okay? So the distance it travels is a vector displacement distance from AB is s equal to the vector AB. So this vector from A to B. Okay? That is the vector of the displacement, changing of the displacement, or the vector of the distance. So if you have this formula, right? So v2 squared minus v1 squared equal to 2as. So what is the acceleration of the objects? Free fall acceleration, right? G, very good. Vertically downward. So in this case, this is a scalar product between two vectors. So vector G and vector S, they are pointing in the same direction. So this you are equal to 2 G S. And what is S? For example, the height it 1, 2. Okay? So S equal to 1 minus 2. So we have V2 squared minus V1 squared equal to 2 G 1 minus 2 V2. So now you move 2 to here. So you have V2 squared divided by 2 minus V1 squared divided by 2 equal to G81 minus G82. So now I multiply mass in both sides, M. Okay? Then I have M V2 squared divided by 2 minus M V1 squared divided by 2 equal to M G81 minus M G82. So now I move 2 on one side and 1 another side. So I will have 1/2 mv2 squared plus mg82 equal to 1/2 mv1 squared plus mg81. Okay? So what do you think? So this guy in the second position equal to the same of this quantity in the first position. So it means that 1/2 mv squared plus mg8, where it is the height of the object. It is constant, right? It doesn't change during the motion. It doesn't change during the motion. And this quantity you call is the total energy or the mechanical energy. Total energy or mechanical energy you define as 1/2 mv squared plus mg8. So in this case, this guy is called the kinetic energy. Okay, and U is the potential, is mg8. So the potential energy is calculated by mg8, where m is the mass of the object, g is the free fall acceleration, 8 is the height of the object with respect to the ground. And you have E conserved. So E conserved means, so here if I consider this formula, I will have K2 plus U2 equal to K1 plus U1. So if I move K in one side and potential in another side, what I have? K2 minus K1 equal to?
U1 minus.
Very good. U1 minus U2. U1 minus U2 is minus U2 minus U1. Okay? So the final K minus the initial K equal is delta K. The changing in the kinetic energy is equal to the minus changing in the potential energy. The minus side means if you increase the kinetic energy, you will decrease in the potential, and vice versa. If you decreasing the kinetic energy, you are increasing the potential. So I repeat, the minus side have the means that if you are increasing the kinetic energy, you are decreasing potential, and vice versa. If the kinetic energy is a decrease, you are increasing the potential, and some of them equal to 0. Okay? Some of them is 0. Means energy conservation. Okay? So some of them is constant. So if you increase this guy, another guy will decrease the same amount, making the total of them is constant during the motion of the object. Okay? That is energy conservation. And the energy conservation I absolutely derive using this formula. Okay? So here, what do you see in this when I derive this? I assume A equal to?
G.
What does it mean I assume A equal to G?
It's a free fall.
Free fall motion. Free fall motion means you need like air resistance, no? Right? Air resistance and any friction. Thus free fall motion. So that the total acceleration of the object equal to the free fall motion. Otherwise, obviously, in this case, A is not equal to G. So we have this? No, right? A is not equal to G. So you should have some difference, which we learn later. So be careful with this example. I repeat again. in this example, you need to assume that the object is thus free from motion. You neglect air resistance and any friction made during the motion of the object. You have to neglect it. Alright? Otherwise, not correct. So now, in another case, in general case, it's not free from motion, but in general case, if I consider the motion of some objects is moving like this, some object moving like this. So the object is here. So this object is acted by many force, for example, but the total force acting on the object is F. So F here is a resultant force of many forces acting on the object, F1, F2, etc. Okay? Many force, but I care the total force acting on the object. So the work done by a force is, what is the definition? The work done by the object. So I have here the work. In the simple case, I'm considering the object is sliding on the floor, and it is acted by some force F. Okay? And it moved from this position, right, to another position. So this is a horizontal. This position is B. Okay? So the object moving from A to B. The force F creates an angle alpha with respect to the displacement. Okay? So in this case, we define the work done by the force F equal to the scalar product between F and S. The scalar product between vector F and vector S. Vector S is a vector AB. Vector changing of the displacement. So AB is this from A to B. So S should be pointing from A to B. Alright? So with the scalar product, what is it? Magnitude of F multiplied by the magnitude of S multiplied by the cosine of the angle between these two vectors, cos alpha. So from this formula you see that if alpha equal to pi over 2, if F is perpendicular to the displacement, so what is the work done? Cos pi over 2 equal to cos pi over 2 equal to 0. Very good. So if alpha equal to pi over 2, the force is perpendicular to the displacement, then the work of the force will be 0. Alright? The second case, if alpha smaller than pi over 2 greater than 0, so cos of this angle is positive. Okay? So the work done by the F is a positive. And in this case, you call done. work done by the force. So I need some more space. If alpha greater than pi over 2, smaller than pi, so F is like this. So in this case, cosine is a negative value. Okay? So the work of the F is a negative. And then in this case, you say the work against work against the F. Because in this case, the F is restrict the motion of the object. And in this case, it creates the motion. It's a restricted motion. And here, it doesn't move. If you act some object, if I act on this, it doesn't move along on the table, right? So if I move it like this, it's moving to the right. And I move like this, it's going to the left. Alright? So you have three cases. Alpha greater than 0, smaller than pi over 2, the work done by the force. Alpha greater than pi over 2, smaller than pi, you have the resistant force. And in this case, you say the work against the force. For example, you have the friction. The work by friction is called the work against friction. Okay? That's the definition for the work. So now I go back to this case. When the object acting by many force, so the work done by the total force will be equal to the work done by F1 plus the work done by F2 plus. Is it okay? When you have many force acting on the object, the work done by all the force in the object, you make the sum over all. You calculate one by one, you make the sum. That is the first case. The second way is work total equal to the work of the force equal to F multiplied by the S. So you sum over all the force, and then you consider this F total, and the work done by total is F and S. So for example, this case, you have F and the displacement, for example, S in this direction is alpha. Okay? So the work done by the force F is F multiplied by S. By definition is the magnitude of F, magnitude of S, and cosine alpha. And we assume the force doesn't vary with the position. So if F is a constant, doesn't depend on the position. So you can prove this. It's called work kinetic energy theorem. So we can prove this, right? So you have, what is the Fs? F is the second law of Newton. You have F equal to ma. So the work by the F equal to Fs, so it's equal to m a s. Okay? And do you remember what is the A's S? Equal to V2 square minus V1 square. The first position to another, the second position. Okay? So you multiply by m, and then you have m. 2as. Sorry. You have the formula 2as equal to V2 square minus V1 square. And now you multiply the mass in both sides. You have 2ma, 2 I give to here. So MAS equal to M V2 squared over 2 minus M V1 squared divided by 2. Okay? So we have what? The right hand side is changing in the kinetic energy. This is K2 minus K1, right? The changing in the kinetic energy equal to the work done by the total force acting on the object. So this is the work energy theorems. So we have the work energy theorems I have just proved. Is the changing in the kinetic energy equal to the work done by all the force acting on the object. Okay? Work of the total, F total. Any question? Okay. So now, if we use these theorems and prove the free fall motion, during the free fall motion, energy is conserved. Please do it. So we go back with the free fall motion. This is ground. Object having the mass m, free fall motion, you have A equal to g, vertically downward. So it's moving like this. Position A, it is here. With the height at A, it's moved to the position B, with B. So using these theorems, find back the energy conservation during free fall motion. 2 minutes. Please do it. Is it clear? Is it clear the question? You can use the work energy theorems to derive the energy conservation during free fall motion. So the work energy theorems say that the changing in the kinetic energy equal to the work done by all the force acting on the object. Okay? Try to do it. Is it okay? Finish? Can you derive it? Alright, so let's do it together. So in this case, we need to analyze all the force acting on the object. So we style force acting on the object. What is the force? Gravity, right? Is mg. Okay? Anything else? No, because the acceleration is equal to g. So you only have free fall motion, you only have the gravitation. You neglect all the air resistance. So now you have delta k equal to the work done by the mg. So the work done by mg equal to what? Mg is going down, the distance is here, so it's mg delta 8 equal to mg 81 minus 82. It's a positive. It's a positive because the gravitational force is the same direction as the changing in the displacement, the direction of motion. Okay? The direction of motion is the same as the direction of the force. That is why you have the work done by the gravitation is a positive, and then you get this value. So what is the delta k? Delta k is k2 minus k1 equal to mv2 squared divided by 2 minus mv1 squared divided by 2. And this one equal to work done by the mg, so it's mg 1 minus 2. So what do you have? So you derive, so finally you have mv2 squared divided by 2 minus mv1 squared divided by 2 equal to mg1 minus mg2. So you have mv2 squared divided by 2 plus mg2 equal to mv1 squared divided by 2 plus mg1. So energy after position 2 equal to the energy after position 1 and equal to the energy, and this is constant. It's conserved. Conserved means it doesn't change during the motion of the objects. Okay? Clear? So far, I give you the definition for the work done by a force. That is a Fs. Okay? So we have the displacement m1, m at the position 1, the force, and it's moving to the position 2, is the direction of motion. So I telling you that the work done by the force is equal to F S. This formula is correct if F doesn't change when you move from this position to the new position. So in case F is a constant, doesn't change with this constant during the motion of the object. So how about the case when F depending on the position of the particles or object? So in this case, for example, you considering this motion from position A to position B, and this the F. The direction of motion is this line, and F depending on the position of the object. So in this case, you have to divide the distance from A to B into many positions, many intervals. And you consider between A and M, two positions, they are very, very close together. You make a displacement is delta, vector delta R. Okay? So the origin is, you remember, in 3 dimensions. This, the displacement at A, the new displacement is Rm. So you are moving from A to M. At A you have the displacement position Ra, this position Rm. So the changing in the displacement delta R equal to Rm minus Ra. So this vector minus this vector, you have this vector. So we have this vector along this. Okay? Delta R is this. Okay? So, because delta R is very small, so A and M, they are very close to each other. Okay? They are very close. Delta R is very, very small. So that you can consider the F doesn't change. F doesn't change from A to M. You can assume that. Okay? So in this case, between from A to M, because they are very close together, so you can consider F is a constant from this position, displacement. So here you have the work done by F. You calculate 1. The first interval equal to F delta R. It's the way we do. Okay? And then next you consider the position between M to N. You have the second also, you get this form. And then you plug it. So the force from the first work done by F, the 2, the second, 3, 4, 5, 6. So each this interval, you calculate the work done, and then you have this. You have N the piece. Okay? So at each guy is the value at this position. The force is F1, and this it changed, so it has F2. So finally, F1 here, and then finally you get F1 delta R1 plus F2 delta R2, etc. You make the sum of all, and then you can calculate the work done from A to B. It's a long distance. Is it clear? So finally, if you consider the work done from A to B is a long distance, you divide this into many parts, okay? And sum over n part Fi of delta Ri. You make the sum. And at the limit, when you divide many pieces, so that these 2 points they are very close together. Limit when n go to infinite, a lot. So this summing is an integral. So you learned already the integration, right? So the meaning of this is the integral of the F depending on position, scalar product with the dr. This is a line integral. Okay? Okay. So in one dimension, this is in 3 dimensions. So in the simple case, you have 1 dimension. You just have a wax. Okay? So then you have the work is the integration of fx dx from A to B. The force F is depend on x. The origin is some point here. XA, XB, okay? At A you have the position XA, at B you have XB. Then you have the work by this formula. So now we derive back the work energy theorems. So that is the work equal to delta K. Okay? So starting from here, you have, because F is equal to the second law of Newton is F equal to ma. And what is the acceleration? Acceleration is the first derivative of the velocity and the second derivative of the displacement. Okay? So acceleration is dv by dt. Is the second derivative of the displacement with time, dx squared, d squared x dt squared. So I can plug to here. F equal to m d squared x by dt squared. So plug to this equation, you have the work equal to F dx. So I have this. M is a constant, right? So dx guy, dx I make is a dx by dt multiplied by dt. So I plug here, this guy is a dx. Okay, so this equal to this. So what is it? This is d by dt of m over 2 of dx by dt squared. Okay? So for example, you put variable t u equal to dx by dt. So d by dt of m u squared by 2 equal to what? Equal to mu du by dt. Okay? So you got this. So what is it? What is the dx by dt? Velocity, right? So dx by dt square is a v square. So inside is mv squared divided by 2. So this one is kinetic energy. So dk by dt. So we have. So from here you have the work equal to integration of dk by dt. Okay? Alright. D by dt of this and dt here. Sorry, dt here. I'm missing one more dt here. D by dt of this multiplied by dt. And this guy is dk equal to delta k. So you have this. Work equal to delta k. So you go back with the work kinetic energy. In the case, the work, the force vary with the position of the object. So you still have the work energy theory. Okay? So you get this guy. You get this formula. The changing in the kinetic energy of the object equal to the work done by the force. So in case the object act by many force, you sum over all the force. You summing over I of many Fi. So then if we have the work total equal to the summing over I of all the work done by many force. So it's work done by F1 plus work done by F2 basically is that. Okay? In case you have many force, you sum over all. And then you have the work total. So now we move to the potential energy. So the potential energy is the energy associated with the system of the objects. So the system of the object consists of two or more objects that exert the force on the other. Okay? So for example, we have the policemen. So this system of particles, they are colliding each other. So the first case, you have the gravitational potential energy. We already mentioned. So the gravitational potential energy is the potential energy of the object and Earth's system. So that is the interaction between the objects. and the Earth. And from this system, the force, gravitational force, and under this gravitational force, it pulls some energy. It's called the potential and gravitational potential energy. The formula is, I denote is UG equal to mg8. The mass g and the height with respect to the ground. So before we already proved that the work done by the gravitational force, so the work done by mg equal to minus u, right? So when you're falling from this point to the lower point, so the gravitation done the force, done the work. But how about the potential? It decreases because it's decreased. So when it done the force, it decreases and it's pressed by the minus sign. Okay? So this initial position, this final position is equal to the minus delta UG. So it's minus UF it minus UR. That's me. UG is gravitation. G is denoted for the gravitation. Only the difference in the gravitational potential at the initial and final location make that matter. What does it mean? So this equal to mg8 final is I minus 8f. It's I, it's f. So it depending on the height only. So for example, you have this case. You have the incline. So the object is moving from this position to another position. Initial place, final place, along this. But how about the potential? Potential, you care the height. So is it I, this it F. So in this case, the work done by the gravitation equal to mg8I minus mg8 So whatever the direction of motion, trajectory, the work done by the gravitation depending on the height, initial height and the final height. And the more complicated case, if I am moving more complicated this case, from this point to this point, the work done by the gravitation is equal to the changing, the difference in the potential at I to AP. It doesn't depend on the way you go, right? It only depends on the height of the first position to the height of the final position. That is the properties of the gravity. That is later you will know this is a conservative force. So the work done by the force doesn't depend on the trajectory of the object. It only depends on the height. From this point to the final point. So you're moving this, or moving this, or moving around, or moving, the work is the same. Okay? That is the special properties of the gravitation. So that is a conservative and non-conservative force field. So the conservative force field, if you consider the case, if the object moving from A to B by two ways. The first way is this line, and the second way is this line. And from this line, the work done by the force is W1, and this is the work by the second way. So if W1 equal to F2, W2 means the work done by this force doesn't depend on the path. Okay? So in this case, F is called the conservative force field. And the gravity is an example. Alright? It doesn't depend on the path you go. Whatever. Or you go directly. It's the same. The work is the same. It doesn't depend on the path you go. You think this path, maybe you take more work, but it's not correct in this case. If work 1 not equal to the work 2, then F is a non-conservative force field. So now you know the definitions for the conservative force and non-conservative. Okay? So the conservative force, when the work done by the conservative force, it doesn't depend on the parts of the objects. Non-conservative, it depends on the part. If you go this part, it's not the same as this part. So in this case, you call non-conservative. For example, of non-conservative is friction. Friction, if the part is longer, of course you lose more energy, right? So, conservative and non-conservative force field, you will have, in case of the conservative force field, you go from position A to position B, part 1 and part 2. If I go one loop, I go from A to B and then go back B to A. So I consider a closed path. A to B and then I will go back by this way. It's the same. So what is the work done by when I go from A to B and then go back A? I consider the changing, the contribute of this work. What is it? The work done by the force. Okay? So this work done by the force equal to the work when I go from A to B. The work from A to B plus the work from B to A. So the work from A to B is the integration of F dr from A to B and F dr from B to A. From A to B is W1. Work from A to B equal to W1 in the previous case. And how about B to A? When I go opposite direction, I will have W. For example, this, I go from A to B by some line. So the way I go work from A to B will be equal to minus if I go opposite direction. Okay? Minus work if I go from B to A. Agree? So in this case, work from B to A equal to, if, so from previous case, work 2 is the work from A to B. So now from B to A, the second line, it should be minus work 2. Okay? So if the force is a conservative, you have W1 equal to W2 and then you have 0. So in case of the conservative force field, if you go by the closed loop, the work done by the force will be 0. In case of non-conservative force, then the work done by a closed loop is not 0 because W1 different from W2. So this is another way to define the conservative force field and non-conservative force field. Okay? Conservative force field, when you make the closed loop, you don't work, you don't no work. But non-conservative, you're still doing some work, it's not clear. Now we move to the part is conservative force and potential energy. The relation between the conservative force and potential. So you consider a body moving in the conservative force field, F, and so it's moving in this field. Okay? From A to B. If you pick arbitrary points O here in this field, and then you define this something is called origins. Origins. You pick any force, okay, maybe this point you can take outside to be more general. Oh. So when you at the position A, you have the position A, position B, you have B. This is a displacement. Okay? So at the position arbitrary, you will have the potential. Potential U at the position R equal to minus integration from O to R of F dr. So F is like this. F acting on the object is like this. Okay? F dr is here. Dr is the direction of motion. Direction of motion for each any points is a tangent to the point, because that is the direction of the velocity. Remember? Direction of the velocity is the direction of motion. So here is dr. Dr is here. So we get this formula. Okay? So from this definition, you say if the potential when R assigned with O, you denote is U and O will be integration from O to O F. You don't have the displacement, so this should be 0. Okay? So the potential at the origin is 0. So this way, you choose the origin to calculate the potential. If the force is a conservative, you have UR defined is unique in the conservative force field, because in this field, the work of the field depends only on the fixed point, but not the path taken between them. So you go from O to R, you can go this way, or you can go this way, or you can go this way, whatever, or to here. They have the same work. F dr, this integral get only one value. Okay? So if you go from O to R by this part, the work done is U R. By this part, still U R. And also this part, very complicated, and go back here. So the work done is still. So it doesn't depend on the part, but only depend on this position with respect to this. So it's still UR. It's unique because it doesn't change when you vary the part. That is the first notation. Okay? So now if you consider the object move between A and B, A, and B. Between A and B. So the kinetic energy theorems you have delta K AB should be equal to the work from A to B. Okay? So what is the delta K? AB, this is a KB minus KA. The work AB, you go from A to B. Okay? That is the integration of the F dr from A to B. This is the definition, by definition. So, I need some more space. So the work when you go from A to B equal to the integration of F dr when you go from A to B, by definition. So what is it? This integration, you already learned the integration, right? You know the integration? Okay. So this equal to from A to O F dr plus from O to B F dr. And then you go back with this definition. From O to some position is the U at that position. So from O to R is equal to minus O to A F dr plus O to B F dr. So what is it? Minus UA, minus and minus. So you have U at A, this minus U at B. So finally you have delta K. So can I remove it? Okay. So finally you have delta K from A to B equal to the work from A to B. This equal to U at A minus U at B. Okay? UA minus UB is minus delta U AB. Okay? When you make the delta means you take the final value minus the initial value. So it's equal to minus UB minus UA. Because you are considering from A to B. A is the initial place and B is the final place. So finally you get delta K equal to minus delta U. So delta K plus delta U is 0. You have what is it? Energy. Energy is conserved. Okay? So the energy is the sum of the kinetic energy at A plus the potential energy at A equal to the kinetic energy at B plus the potential energy at B. And it is a constant. And U presents some form is the potential energy. So at this point, you know origin of what is the potential energy. So who can tell me the definition of the potential energy? What is the definition for the potential? Depend on the position of the particle in the field. But it doesn't depend on the part. You go from this point to another point. And the definition is formula 3.1. So you take O is the origin to calculate the potential. So origin is the potential is 0. So the integration of the force acting on the object. So the work done by the force of the objects to bring the object from this point to this point equal to the potential, but opposite direction. Okay? Okay, so conclusion, you need to remember this formula. Potential of the object at this position equal to the work done by the force, conservative force. When you bring the object from the origin to that point. For example, you go back with a free fall motion. I make example for you to see. This is a ground. It's the motion of the objects from A to B. The origin you choose is what? Ground. Okay? If you choose O is this point. So what is the potential at A? Potential at A equal to the work done by the gravity. Okay? Gravity is what? mg. When it brings the object from the origins to this point. So the origins mg acting on the object here, it brings the object from here to here. That is the work done when you go from O to A. And now you calculate this work. What is it? Minus side and minus side here. Minus side. So I rewrite it. Minus side of the work done by the force when you go from A to O to A. That is the definition for the potential. And now you need to calculate the work done by the gravity when you go from O to A. This the force. What is the direction of motion? O to A. So it should be mg. The work is the force multiplied by S. Okay? And what is the vector S? You go from O to A. S. So how about this angle between these two vectors? Pi, right? So the value here is mg multiplied by S multiplied by cosine of which angle? Pi. Cos pi equal to minus 1. So this minus ms. What is the S? S equal to the height of the object. Okay? So this minus mga. So I plug to this formula. I have potential at A equal to minus of minus mga equal to mga. Okay? So if you use this formula, you can calculate potential of the object at the height of A. From high school, you will solve it, you will set it, and you don't know why you get it. What? You don't understand what is it. The teacher just going there, okay, and when you calculate the potential, you just make mga, that's it. And you don't know why is that. What? Now you know the reason. Because the definition for the potential is the potential at this point equal to the work done by the force when this force brings the object from the origin to this point. Of course, you can choose the origin is anywhere. Okay? In case you choose at the ground, the potential is mg8. But another case, you don't like, you choose another point. What happens? Right? Exercise code. If I don't choose the origin here, I choose origin higher, always here. So what happened? If O is here, origin is here. So still we follow this formula. So in this case, you calculate O prime, okay? The work from O prime to A. Mg is here. S is from here to here. Okay? So in this case, what is it? Mg and S, they are pointing in the same direction. So the work from O prime to A equal to Mg A2. So if you plug, now you calculate potential at A equal to minus work from O prime to A equal to minus MgA2. So how about this value and this value? This value, UA now is minus MgA2. A2 is this distance. They are not the same. But still, the potential at A. Alright? So what does it mean? It depends on the origin. If the origin is at the higher level than the point you consider, so in this case the potential is negative. And then if it's higher than the origin, it's positive. So it depending on the position you choose the origin, and it doesn't matter. You can choose whatever you want. But when you choose, you need to calculate correctly the potential. Okay? Otherwise, it's not correct. So it's not always MgA, right? MgA is one case. Another case, you choose the origin is here. What happened? So in this case, it's minus Mg, A is different in the distance. Clear? Okay. Okay. And when you consider the motion of the object, when you choose the origin, you need to be fixed. So you can choose any points in the field, whatever you want. But when you already choose, you need to fix it. You cannot change the origin. This time you choose the origin, another time another. It's not correct. You fix it. Okay? Okay, so this part is keep this. So similarly, you have the elastic potential energy. Another case, you have the elastic force. Also elastic force on the spring. Alright. So you have the springs. Okay? So it depends on the position. Here and then it's moving around, so it's depends on the position x. So elastic force is minus kx. So in this case, you still have the work done is like this. So this part you read at home, and then you will get the relation between the force and the potential. The force is the first derivative of the potential with respect to x. Similarly to the gravitation. So the first derivative of the potential. So potential is kx squared over 2. So the force is du by dx equal to minus kx. Minus sign because the x to here, so the force is the opposite direction. Okay? The conservation of the mechanical energy is, you have this. Okay? Sum of the kinetic energy and potential energy is at the initial position equal to the kinetic energy plus potential at the final position. So what happened in case? So in case the object is acting by only conservative force, you have the energy conservation. So in case you also have non non-conservative force, what happens? Okay? Non-conservative force. So for example, you have the force total. Force total equal to F1, F2, many force acting on the objects. So you have the object, you have many force F1, F2, F3, F4 is gravitation. Many force acting on the object. You sum with the sum all. So in this total, you separate two force. So you sum over all the force is the conservative force. Conservative force plus F non-conservative. Non-conserved and conserved. Okay? You separate two types of the force. Conservative force you sum with other. Non-conservative you have this. And non-conservative, okay. So you use the work energy theorems. What do you have? Delta K equal to the work total. Okay? Work total is the work done by the total force. So it should be work by the F conservative plus the work non-conserved. Okay? Work conserved and non-conserved. And you know already work by the non-conserved quantity is equal to minus delta U. Potential. Okay? You always have work G equal to minus delta U, minus side. So you change to here, you have delta K minus delta U equal to work of non-conservative force. And changing of mechanical energy is delta E equal to the work of the non-conservative. So the non-conservative, you have two cases. You have applied force. Applied force means it's object I push it. And the friction. Okay? Another case, you have friction. So in this case, so of course from this formula, in case of the applied force, you have the work of the applied force equal to the changing in the mechanical energy. Okay? If you don't have applied force, the energy is conserved. If you have applied force, it's the changing in the mechanical energy. Okay? By the friction, you also have similar. Delta K equal to the work done by the friction. And you know that the friction is always this as direction of motion. Friction is always opposite to the direction of motion. So the work done by the friction is always negative. So the changing in the mechanical energy equal to the work done by the friction, and the work done by friction is negative, making delta E negative, making the energy decrease. So in this way, energy decrease. And in this case, applied force is a positive work, so it's positive. So in this case, the energy of the object is increased. Okay? Alright, so we have any question? Is it clear? So, conclusion, you already have changing in the kinetic energy equal to work done by all the force is not conservative, right? No conservative force, no friction, or no applied force. You have energy conservation. Energy doesn't change. If you have only applied force, energy increase because the work done by the applied force is positive. If the work done by the friction is negative, making the change negative, and change negative means energy decrease. Alright? So I provide this exercise from the energy and energy conservation. You can do the exercise to more understand this theory. Okay? Okay. So I remind you from the circular motion. I have two exercises. Did you do it? Did you do at home? This one? Did you do it?
Yes.
Yes? You get the answer?
Yes.
Very good. How about this one?
A little bit difficult.
Okay. So I give you the hint for this exercise, okay? So you consider the vertical circular motion. This like this. So the roof of the bucket fill the water. So we have the bucket. So into the bucket you fill with the water. And many positions. Okay? So you consider the water inside the bucket. Only the water inside the bucket I denote as the mass M. And you analyze the force acting on this bucket. What is it? In this case. Which force? In this case, mg, gravitation, and no more contact force between the water and this part of the bucket. Agree? This is a normal contact force. So in this case, you have gravitation and normal contact force. Okay? Normal contact force is like this, the water inside the bottle. So you consider the water inside the bucket. The mass M. The force acting on this object is mg plus n. And the second law of Newton giving you ma. So here, n mg equal to ma. So now, because this bucket is moving circular motion, so it should have some acceleration, centripetal acceleration. So I resolve this vector on the radius over here, the radius axis. Positive direction forward, the center of the circle. So what I have? Assuming that this angle is theta. So this angle is theta. So we have minus mg cosine theta, this part, okay? Minus mg cosine theta plus m equal to centripetal acceleration. And what is the centripetal acceleration? Radius at this point. Okay? So from here you can extract the information for n equal to mv squared plus mg cos. Is it okay? So the condition for the water is not falling down. What does it mean? The water inside the bucket not falling down means the water still stick to the bucket, So in this case, what does it mean? To the bucket, and n should be greater than 0. Very good. So the condition for the water staying in the bucket is n should be greater than 0 for all the value of the theta. So when you change the position, the theta, this angle changes, theta changes, and the highest place, what is the value of theta? Pi. Very good. So from this condition, you have mv squared divided by r plus mg cos theta greater than 0 for all theta. This correct for all theta means the mean value of this should be not greater than 0. The mean value corresponding to the case cos theta equal to, so cos theta greater than -1, smaller than 1. So the minimum value is -1. So when the minimum case, you have v squared divided by r minus mg should be greater than 0. So cosine theta -1 at this position, when the theta is pi, cosine is -1. The highest place. If at the highest place the water is not falling down, then the water is all the way inside the bucket. Okay? So we have this condition. So from this condition you have v squared greater than mg r. So now you can calculate the minimum speed. Minimum v minimum square equal to mg r. And you plug the number in. R is 1.2 mass. You don't have the mass? Sorry, not m anymore because m go away, so I don't have m. So this equal to multiply 1, 2. The result is v mean equal to, what is the result? Calculator. Who has the calculator? 11 but square root. 3 phẩy mấy? Alright. 3.43 meter per second. It's okay now? Alright. So we stop here. Alright, so we stop here and then stop for our course. Thank you very much for your attention to my course. And good luck for the exam. And I expect that I will see you next year for this course. Okay? Remember.
không hiểu là gì. Đi đi tí anh trả 10.000 không thôi. Đi tí anh trả cho 10.000 không thôi. Mất. Mất 20 rồi. Đi cùng đi. Đi cùng mới ra đây rủ. Không.
Mày thấy cùng đi đâu? Tao như của ai?